Good morning, good afternoon, or good evening, depending where you are. This is Tom Layden, VP Marketing with Excelero. Welcome to the 5th Excelero webinar of 2020, the third one in our AI series. I'm very excited that we again have such a large audience, so thank you all very much for returning to these webinars. We're trying to make them interesting for you. For today's webinar, we have three speakers. Our first speaker is Amri Geller, CEO and co-founder of a company called Run AI. Amri is renowned authority in the field of containers, orchestration, and AI, and he's got a very interesting presentation for you. Next, we'll have Excelero's Gil Witzinger, who joins Amri to discuss Excelero's CSI Driver for Kubernetes. Gil is a software engineer in the management team at Excelero. And then next, we have William Benton from Red Hat, who will discuss Open Data Hub, the data and AI platform for the hybrid cloud. Before I hand it over to Amri, here is some logistics information. We want this webinar to be very interactive, and I would like to get many questions from you guys. So here's how this works. Everybody but panelists will be on mute, but at the bottom of your UI, you should see a Q&A button. Post as many relevant questions as you want. We have a team of specialists ready to answer those questions in real time, and we will take the best questions at the end to have them answered live for the whole audience by the presenters. For now, sit back, relax, and enjoy the webinar. Amri, the floor is yours.
Thank you, Tom. Hi, everyone. I'm Amri, co-founder and CEO at Run AI. Going to share my screen. Yeah. Okay, so we're going to speak today about Kubernetes for AI workloads. And I'm going to speak a little bit about the history of virtualization, and then about Kubernetes and how AI workloads is using containers, and then about how to build a better compute workflow for AI workloads on top of Kubernetes. So in the history of virtualization, data centers moved from using bare metal servers to what we're all familiar with as the virtual machines, which helped a lot with flexibility, utilization, and manageability of workloads in data centers. And in recent years, we're seeing containers growing in the adoption within enterprises. Containers scale are a new type of virtualization. They scale easily, very lightweight, and can be reproducible and portable between different cloud environments. Is it on-prem or is it on cloud? And in current data centers, there are already hundreds, thousands, and millions of containers that are running concurrently. And therefore, in order to run those workloads, you'll need an orchestration system that will manage all those containers running concurrently in data centers. As the orchestration is needed, here comes Kubernetes. So part of you might heard about Kubernetes, which is basically an orchestration system that helps with managing all those containers that are running within data centers. It helps with tracking, scheduling, and operationalizing containers at scale, as well as having an efficient utilization of cluster that's running huge amounts of containers in parallel across different clouds and different environments. Actually, today, 60% of those who deploy containers already use Kubernetes as the orchestration system, and this is growing really fastly, and the adoption is growing within enterprises. Now, I'll be happy to tell you more about AI and how this is related to Kubernetes. So the first thing is that, like Kubernetes and containers, AI is growing significantly within enterprises as well. And what actually fuels the development of AI algorithms and solutions within enterprises is computing power. It is already known today that in order to solve more and more complex problems using AI algorithms, you'll need more and more computing power, where the state-of-the-art algorithms such as deep learning and neural networks need to tune billions of parameters, and that requires tremendous amounts of compute. In order to support these computational efforts, data centers are going through a transformation. And the first thing is that data centers have new accelerators, new processors that are purpose-built to support these compute-intensive tasks of AI, such as the GPUs or new accelerators that will enter the market soon. Another way to run this compute-intensive workload that is very efficient called distributed computing. Since those workloads of AI are highly compute-intensive, many times users run a single job on many accelerators in parallel in order to accelerate the process of the workload. And lastly, when we look on AI development, the R&D of AI engineers is based on experimentation, on running experiments. So as an AI engineer, in order to build solution, I run experiments, and I run many experiments in order to progress. That fact that data centers are now having those new accelerators and the experimentation type of R&D, where every user runs a variable amount of experiments at every moment, leads to coupling between the data scientist and the hardware accelerator, so that in today's environments, every researcher or data scientist gets a specific amount of resources, and then that leads to a fact that if they need more resources than what they get, they cannot do it, and therefore they can't run more experiments than the number of resources that they have. And when they are not using their GPUs, nobody else can use it, leading to underutilized GPUs, bad ROI on GPUs that we acquire to our data centers, which basically leads to frustration on both sides, where the data scientists that are an expensive asset for the enterprise cannot run enough experiments, and therefore their productivity and speed slows down. And on the other hand, IT organizations that buy this expensive hardware, such as the GPUs, cannot have any way to efficiently utilize the hardware and make the most out of it. When we look on the problem from that angle, we understand that what is missing is an orchestration system that will help data scientists to run as many AI workloads as they can at every moment, while the IT administrators will have a tool to manage those GPUs efficiently to get the maximum utilization. And now we can start and think how such an orchestration system would look to orchestrate those AI workloads on the new accelerators, such as the GPUs. In order to do that, we need to look on how AI workloads are used and how AI algorithms are developed. And when we look on it, we see that AI engineers heavily using containers. So container ecosystem is growing really fast for data science, with a lot of frameworks such as TensorFlow and Keras that have a lot of versions that containerized environments help run, as well as tools such as Kubeflow that was built on top of Kubernetes to support the needs of data scientists. In addition, NVIDIA, which is developing the GPUs, has their NGC, which is a repository with pre-built Docker containers that help data scientists to start experimenting really fast. So all the containers ecosystem is growing really fast and heavily used with AI. And therefore, when we'll think about orchestration and how to manage our resources, the first thing that will come to mind is Kubernetes, as we explained earlier, that purpose-built in order to orchestrate containers. Therefore, we might think that Kubernetes can solve the problem and help us manage the resources efficiently when running AI containers. However, Kubernetes, which is, as mentioned, the de facto standard for container orchestration, was built in order to run services workloads in production and not the AI workloads that are being run in research today. The fact that he was built for that, it lacks important capabilities when you want to run AI workloads, and that's managing multiple queues of workloads, helping with automatic pause and resume of workloads that is running on the cluster according to priorities and policies in the organization, as well as capabilities to make high-performant workloads run on the cluster with capabilities such as topology awareness, where you can match the right hardware for the right workload, as well as efficient management for distributed computing workloads that is highly used with data science, as mentioned earlier. Therefore, implementing Kubernetes will not solve the problem of AI engineers that want to run much more experiments on the cluster to be productive, and IT organizations that want maximal ROI on their GPUs. In order to understand how we can improve the resource management and make a solution that is suitable for AI workloads, we'll need to get deeper into the workflows of data scientists and AI engineers, and what it basically means experimentation, that is their day-to-day work. For that, we need to distinguish between two types of workflows of data scientists, one called build and the other is training. Let's start with the build. Build is the part where the AI engineer and the data scientist actually building an AI solution. It is he or she codes the model, making sure that it can actually start and learn. So there is a lot of interactive sessions. They try, they debug, they tweak the code until it actually works. And therefore, in this type of workflow, the data scientists have short cycles of interaction with the accelerator, with the GPU. The performance is not important because the purpose of this part of when you build a model is just to bring it to a state where the model can start and learn. And therefore, the utilization of the GPU is low. However, once the model is being built and the code is ready, the model is now ready to start and train, which means it is ready to start and learn. In the learning process, which we call training, the model starts to process huge amounts of data, all the data sets. And therefore, this is the process that can take from hours to days to sometimes weeks, where the AI engineer just run a job, let it start, try and learn from the data. And therefore, in this case, we want high throughput, meaning process as many samples as possible at every second. We want high GPU utilization to make this long process short. And we can actually do this process in a remote execution. We can send, as a user, I can send my training job to remote execution on a cluster. And this execution can take, as mentioned, a lot of time. So again, if we're looking on those two workflows, one of them is the build, is the beginning where you just build a model, and then when you start to train the model, that is the high performant part of the workflow. When we understand that data scientists have those two types of workflows, we can try and think how we can match the resource management layer with those two different compute characteristics. For that, Run AI came with a concept called guaranteed quotas. In order to understand what is guaranteed quotas, I'll start with explaining what is fixed quotas. And this is basically what we're all familiar with, that every user gets a specific amount of resources. For example, if I'm sharing 4 GPUs cluster with my peer with fixed quotas, I can get 2 GPUs and my friend can get 2 GPUs. The problem here is that if my friend is not using his or hers 2 GPUs, I cannot use it, and therefore GPUs would sit idle. However, the advantage here is that those GPUs are always available for each of us, and therefore such concept such as fixed quotas is very suitable for the build type of workflow, where as a user, as a data scientist, I need to interact frequently with the GPUs, and I need it to be always available. But we can do much better in order to improve the utilization of the cluster and provide researchers and data scientists a better way to run experiments on the cluster. With that, we can use guaranteed quotas of Run AI, which is basically allows users and data scientists to go over their quota. So if one user will not use his or her GPUs, other users can use it at the meantime and run much more experiments. More experiments when it comes to data science means better data science, means faster time to solution. And of course, it also improves the utilization of the cluster. So this type of workflow, this type of quota is very suitable for the training part of data science, where a user just sends jobs for processing, a very long and compute-intensive jobs that can take for weeks. But as a user, I can send it to processing and send as many jobs as I want in order to run more concurrent experiments at the same time. So if we would look on a schematic description on how such a system could look, we can imagine a system with several queues where we're taking all of our GPUs in the data center and divide it into two logical groups of GPUs. One is called the build environment, and the other is the training environment. In the build environment, we'll provide a fixed number of GPUs for every user so that at every moment, the user can interact and build models. So at every moment, if I'll need a GPU, I'll have a GPU that I can run and build some models, some new models. But then all the rest of the GPUs would be pulled together to what we call training environment. And then all the users can submit jobs of training to a very large pool of resources. And if there is free capacity, as a user, my jobs that I submitted to the queue can run. But if all the GPUs are in full utilization, then comes to play priorities and policies mechanisms that understand which jobs should run at every moment. And we need to implement a mechanism for pause and resume of workloads. With this type of mechanism, we can make sure that at every moment, every user has a GPU to build new models, and easily they can send jobs for long training compute-intensive workloads that are running on the cluster, but the system will know automatically how to manage those workloads and manage the scheduling and the orchestration of those workloads. So once we understand how an optimal compute workflow for AI workloads can look like, we can make it all work together in the new data centers that has, first of all, the new accelerators, the GPUs, or the new ASICs that are in the market. They must have a fast storage solution such as Excelero, and they will talk about it next, and also fast networking to connect between the servers to make sure that distributed computing workloads that run on many GPUs in parallel can run efficiently. On top of that, you'll need an orchestration system that is utilizing efficiently those resources. And for that, Run AI bring a cluster operation system that stitches all together and make it work as a high-performant AI data center. We do that by bringing concepts of those multiple queues as described that are familiar for some of you from the world of high-performance computing. We bring it to the new world of Kubernetes and the growing ecosystem of data science and IT around Kubernetes. With that, we can actually bridge the gap between what data scientists need and what Kubernetes and IT can provide in the new data centers, the new GPUs. Data science teams will gain full productivity and speed and innovation, and IT teams will get maximal GPU utilization. The Run AI system is able to manage workloads that are running across multiple clouds and multiple clusters in an integrable way so that data scientists will keep on running workloads as they're used to, and IT organizations will use Kubernetes as the growing ecosystem for IT with full monitoring and control. I want to share with you also a case study that we did with Run AI, where we help an enterprise make their data center much more utilized and, of course, have better data scientists. So this is a large enterprise with large deep learning team that build deep learning models. They had GPUs on premise where they shared the GPUs between all the team members, and they felt that they keep on buying GPUs to the data center without getting a better productivity from the data science teams. When Run AI first interact with this customer, we gained the understanding that they're actually utilizing only 28% of their GPUs, of the GPU of the cluster. And while some users wanted to use much more compute than what they had, other users left their machines idle, which led to low utilization and low productivity. In addition, the enterprise had plans to buy more GPUs in order to satisfy the data scientists that felt that they don't have enough compute. But actually there was enough compute and those data scientists could run much more experiments. And when we implemented the Run AI queuing mechanism on top of Kubernetes, the utilization of the cluster grew to 73%. It was significantly higher ROI on the cluster and much more experiments, double the number of experiments per GPU, which means better data science, because as a user, I can run much more experiments, and it made the life of the data scientist much more simple. So before we end, just a little bit about Run AI. So we are a company that founded in 2018 with offices in Tel Aviv, New York, and Boston, working with Fortune 500 companies as well as leading academic institutes. And what we bring to the table is help enterprises build their AI infrastructure and helping researchers and data scientists to be much more productive, reduce time to market, and help IT organizations improve GPU utilization and their AI data centers using Kubernetes. Thank you.
Omri, thank you so much for this great presentation. That was very enlightening. Thanks so much. Folks, please post your questions in the Q&A section. We're very happy to get your questions, and we will have Omri answer some of those questions at the end of this webinar. Next up is Gil, who's going to share a few words about how we integrate NVMesh with Kubernetes. In the meantime, there is a quick poll question that's coming up. So if you would be so kind to answer that one, or let us know if you're just here to learn, that's also fine. In the meantime, Gil, why don't you share your screen and get ready to talk about NVMesh and Kubernetes. All right, Gil, I think you can kick it off. Go ahead.
Yes. So hi, my name is Gil, and I'm a software developer in Excelero. And I'm going to talk to you about our NVMesh CSI driver for Kubernetes. So NVMesh CSI Driver is basically a plugin for Kubernetes that allows us to use NVMesh as a storage backend for Kubernetes. So that from Kubernetes, you could create, manage, and consume NVMesh volumes. The main features of the driver is that it allows static provisioning. That is when we already have a volume created in our NVMesh backend, and we want to expose it into Kubernetes and use it in Kubernetes. It supports dynamic provisioning, which is when a user in Kubernetes requests storage of type NVMesh, and then Kubernetes will contact the CSI driver and then create a volume on the NVMesh cluster and expose it back to Kubernetes. We support both block and file system volume. So if your app requires a block device inside a container, you can do that. If it needs a file system, we can do that too. The driver just attaches a block device and then creates a file system on the device. We support all of Kubernetes access modes, which are read-write once, read-write many, and read-only many. And we support extending volumes. We also support extending volumes live, so that you don't need to stop your pods or you don't need to turn off your workloads. You can extend the volume while the volume is attached and mounted to pods. And at last, using NVMesh volume provisioning groups, this allows us basically to create different volumes for different workloads. And we can create those in NVMesh, and then we can use them with the CSI driver. A bit about architecture. The driver has two main components, the controller and the node driver. Both are running as pods inside Kubernetes. And the controller actually communicates with the NVMesh management using REST API. It is in charge of creating volumes, deleting volumes, and listing volumes mainly. And the node driver runs as one instance per node. It will run on each node, and its job is to communicate with the NVMesh client so that it does the job of attach, detach, and also a few internal mounts that I will show a bit more about later. The NVMesh targets in the solution could be a separate storage server, but they don't have to. They can be also installed converged on the nodes next to the NVMesh client, and then they can use the drives that are available on these nodes, and then you don't need dedicated storage servers. I'm going to go over a flow of creating a volume in Kubernetes, a persistent volume claim, and then creating a pod, and then we see how everything what's going on in the driver. So first, the user creates a persistent volume claim. That in this case, if the volume he requires a volume of type NVMesh, then Kubernetes will contact the CSI controller, and that will create a volume on the NVMesh cluster. When the user creates a pod that uses this PVC, then Kubernetes will first decide on which node it wants to run this pod. And then on this node, it will contact the node driver and tell it to attach the volume and then mount it to a specific path in the file system. So I'm going to show a bit more detail in the next slide. So here we can see mainly we can see here the difference between a block volume and file system volume, and then also see what happens when we mount the volume. So if it is a block volume, you can see the NVMesh client attaches the volume to /dev NVMesh v1. And if it's a block volume, all we need to do is bind mount to some path that Kubernetes gives us, so that later it will expose this path into the container. And in case it's a file system volume, then if it's the first time and it has no file system, we will run makefs and then intermediate mount. And in the next stage, we will do a bind mount to wherever Kubernetes wants this volume. To a very simple example of YAML for Kubernetes, just to show how simple it is to create a volume. First is a persistent volume claim. You can see that we give a name. We say which access mode we wanted to use. Volume mode, as we said, this is block, the amount of storage that we need, and then here, the storage class name, NVMesh RAID 10. This is actually a predefined storage class that when the CSI driver is installed, we install a few of those predefined storage classes just so it will be very easy to create volumes out of them. If you need to create a custom VPG, if, for example, you want to restrict to specific targets or specific type of drives, you can create a custom VPG in the NVMesh software, and then you can just create a storage class that points to this VPG. So again, very short, it says who is the driver, what is the name, and the VPG name that we want to connect to. So for summary, a few benefits of using NVMesh in Kubernetes. First, you get persistent storage that scales for your stateful applications. You ensure that the storage is not a bottleneck. So you get from this also predictable performance. You can scale your performance and capacity linearly just by adding more drives or more target nodes with drives. And the driver also allows us to, it allows to reconnect the volume, or let's say when a pod needs to relocate to a new node, then the driver will make sure to reconnect the volume that the pod was using on the old node on the new node. And of course, using an access mode, you have the choice of choosing which access mode to use per volume so that you can match the storage to the requirements of the application and the file system. And that's it.
Thank you, Gil. Good presentation. Thank you so much. All right, I'm not going to waste too much time. I'm going to pull it to hand it over to Will. Will, why don't you start sharing your screen while we have the audience answer a second poll question.
All right. Can everyone see a title slide here?
Yes, we're good.
All right, perfect. Thanks so much. Just a second.
And now it's gone.
Yeah, let's see here. All right. So I'm Will Benton. I'm engineering manager and an engineer at Red Hat, and I want to sort of talk about end-to-end machine learning discovery workflows and machine learning systems on Kubernetes at sort of a high level. Earlier, Omri talked about Kubernetes for machine learning workflows and talked about build and training workflows, showing how Kubernetes is flexible enough to schedule concurrent experiments on GPUs and improve resource utilization. I'm going to sort of talk about some higher level ways to get self-service discovery environments and to sort of automate sort of error-prone parts of this workflow. So if you think about what kind of steps a machine learning practitioner has to go through to solve a problem with machine learning, you're really looking at like something that looks about like this. You might divide this into more or fewer stages depending on how you see the problem, but really we're starting off by defining what success looks like. We're gathering, cleaning, federating, and labeling data that we can use as examples, making sure that we have the right data sources. We're turning our raw data or data that's in a format that's suitable for application code or databases into feature vectors that we can supply as input to a machine learning algorithm. We're using a model training algorithm to identify good trade-offs in summarizing our training data, producing a function that can make predictions. We're going to test and make sure that that model works as well with data it hasn't seen as with data it has. And finally, we're going to turn this into a production service and monitor it. We'll talk more about why we need to monitor that service later on. Now, this whole process, a lot like the software development life cycle, is iterative, right? There are loops in this process. At any point, you might go back and say, I need to revisit a decision I made earlier because I've discovered something that indicates to me that that decision is no longer the right decision. So anytime you have one of these loops, the latency between these steps can dramatically impact developer velocity or data scientist velocity. Now, when we talk about these problems, the sort of thing that we think about is the model, right? Models are celebrities. You can probably name several different machine learning models, and there's a lot of popular focus on this part of the process and on getting to the model and on the workloads. And that's really essential. But practitioners know that your model is only as good as the features you supply to it, and that model can go wrong in production very easily. And if you don't have a good way to figure out where it's going wrong, your model is just going to be making predictions that are unacceptably inaccurate and impacting your business metrics. And really, that model is just a tiny part of the overall machine learning systems that we use to get business value out of machine learning. And this diagram I'm borrowing from a great classic now paper called Hidden Technical Debt in Machine Learning Systems that shows that really the challenges of machine learning systems are from tying all of these disparate components together and having one place to manage all of these things, one place to sort of coordinate all of these concerns, and a lot of sort of glue that brings these different components together. So the machine learning model itself is an important part of these systems. It's an essential part of these systems, but it's a relatively small part. But it's a part that touches so many other things that it can make the whole system more complex. So let's talk concretely about what some of these systems look like and who some of the personas who build them are. So when we're talking about collecting that data, we're talking about things that are sort of the responsibility of data engineers. We're looking at data from different sources, data in motion, data at rest that's structured, data at rest that's unstructured in file or object storage. And these data engineers are concerned about elastic scale-out, auditability, high availability, having the processing steps that they use be repeatable, and also being able to understand how the system is working overall. You need observability, you need governance, you need really management for these data services. Data scientists, whose job it is to find patterns in this data and exploit them for business value, need on-demand infrastructure. In the past, you've had data scientists become experts at managing their own infrastructure. This is not really something that a lot of data scientists want to do these days unless they absolutely have to. We need to be able to provide self-service experience for data scientists while still meeting the guarantees that we need as an organization about security, auditability, and so on. Repeatability and reproducibility are also huge concerns for data scientists. If you're doing research and no one else can get the same results as you, you haven't really accomplished anything. So we need a way to make it easier to reproduce this work that data scientists do. Finally, when we're talking about building a machine learning system, application developers and sort of DevOps teams put it all together in practice. And this means taking the services that data engineers support and the techniques that data scientists develop and putting it all together in a robust system that solves a business problem. And there are a lot of similar concerns that the application developer persona has. One is that they need a scalable channel for monitoring and managing these systems. They need a way to easily deploy machine learning models as microservices that interact with the rest of the application. They need pipelines for continuous builds, reproducible builds, and they need ways to monitor, test, and route to new versions of services in production. Now, all of these roles overlap to some extent. So we have heterogeneous teams with different and diverse skills that need to work together to build these overall systems. And in fact, even at the level of workflows, all of these teams are working together. The data engineers are responsible for some aspect of collection and cleaning. The data scientists are responsible for these sort of discovery tasks, and the application developers are responsible for these production tasks. So we have really complicated social problems involved in building these systems as well, not just technical problems. And we need to make it easier for these teams to work together and be productive. So I want to talk about some basic features of container orchestration with an eye towards how these help people build machine learning systems. Now, one aspect that's sort of table stakes for a container orchestration system like Kubernetes is the idea of immutable container images. For conventional applications, this is a security and reproducibility benefit that you have a base image with some operating system code. You have the user space libraries that your application depends on, and then you finally have the binary or code that you need to actually run your application. But for machine learning models, this has an additional benefit of reproducibility and auditability. If you're using machine learning to solve business problems in a regulated environment, you may have to go back and say, why did I make a particular decision? If you decided to not write a loan, for example, last summer, you might need to go back and see what model you were using at that point. Because we can refer to these container images by hashes, you can actually go back and say, well, this is the model I was running at that point. We combine these together in a container orchestration platform in stateless microservice architectures. Now, microservices have a lot of technical benefits. They introduce some complexity, but the trade-offs are attractive. One is that you can scale these services up by running them on the same machine. They're all running in containers. They communicate via these well-defined lightweight interfaces, and therefore it doesn't matter where they're running, right? You can scale them up by running them on the same machine. You can scale them out by running them on different machines in the public cloud. If one of these services turns out to be a bottleneck in your system, you have a way to identify it, and you can run multiple copies of that service behind a load balancing proxy. When it comes time to upgrade one of these services, you don't have to shut the whole system down. Instead, you can install an updated version, route some traffic to the updated version, and if the system still behaves appropriately, you can gradually route more and more traffic to the new version until finally you're routing all traffic to the new version. This is actually a really valuable thing for models as well, because a lot of times we want to validate or backtest in production in addition to in our experimental environments. So if we have models as microservices, we can benefit from that sort of gradual rollout of new versions and monitoring. But for all the technical advantages of microservice architectures, another advantage that's really important is the social advantages of microservices. If we think about Conway's law, how software sort of takes on the shape of the organizations that produce it, we could have a really complicated picture for what our software looks like if we're going to be building machine learning systems with these sort of diverse teams that are responsible for the different parts of the systems. By having microservices that are well-defined and have clear responsibilities, it's much easier for these diverse teams to work together. Another advantage of container platforms is that deployments are typically declarative. In Kubernetes, you have a manifest indicating what Kubernetes objects you're going to use in your application and how those things are tied together, rather than having an imperative recipe of step by step, this is how I'm going to set my application up. And we have ways to sort of say that these components are connected and isolated from the rest of the world, but also that we can talk to various components from the outside world by exposing them with routes. The real advantage of this is that it makes it possible for the infrastructure to heal itself, to monitor itself as it goes on. And we'll talk more about that in a minute with the operator concept. Another thing that declarative deployments enable is continuous integration and continuous deployment. Everyone's had code that works on their laptop, but nowhere else. If you work with data scientists, or if you are a data scientist, you probably have received an interactive notebook or an analytic technique from someone or given one to someone else that they can't reproduce either. It's the same problem that we have for all of software. And continuous integration and continuous deployment takes the onus off of, hey, why don't you have the environment that I have on my laptop, to, hey, I'm going to put my work into source control and I'm going to run a test in a controlled environment. And if that test succeeds, I'm going to go on and build a container image, which I'm then going to turn into a reproducible declarative deployment on Kubernetes. This enables data scientists to make their work more reproducible by shifting the focus from maintaining a special environment on one laptop and then trying to reproduce it for your collaborators, to just simply declaring your environment for experiments and production in Kubernetes, and then going on to reproduce it there with the declarative deployments. Finally, because microservices involve a lot of communication and a lot of different services, container platforms have sophisticated support for monitoring these deployments. This is useful for a special problem that we see in machine learning, which is that of data drift or concept drift. And this problem is where data in the real world no longer looks like the data we trained our model on. So if that data that we trained the model on is no longer representative of what we're seeing in the real world, we have this problem where the performance of our model gradually gets worse over time. And this is much worse than the way conventional software breaks, right? If we're lucky, conventional software breaks in an obvious way. It fails to compile, it fails to deploy, it's very slow, or it's crashing in production. Obviously, there are more insidious ways software can break, but if we're lucky, it breaks in these obvious ways. Machine learning models, though, have this really insidious failure model where they might just keep giving you answers, but those answers are going to be wrong way more often than is acceptable. So I want to talk about how the Open Data Hub enables people to get started using these techniques on Kubernetes. And I want to start with a particular pain point that a lot of data scientists face, which is getting that reproducibility and having an on-demand environment. Data scientists love to work on their own laptops, but this isn't ideal for a host of reasons. One of them is that you can't get access to sensitive data that's inside your employer's firewall. Your laptop probably also isn't as fast as a workstation, and you probably don't have as much storage as you need, so you can't work with all the data you like to. Model training is often math heavy, and hardware acceleration can really help, but laptops aren't as powerful as workstations. And finally, a lot of data scientists have Macs, which have GPUs that are great for making Final Cut Pro faster, but not great for accelerating model training. By using OpenShift and the Open Data Hub project, we enable access to better hardware. I can have a self-service environment that looks exactly like the environment I have in my laptop in any cloud, right? Within my company's firewall or in the public cloud. I can have access to scale out for training different models and orchestrating experiments. As Omri talked about, I can scale up with GPUs, and I can get at that sensitive data that I can't bring outside the firewall. The project that we're talking about to make this possible is the Open Data Hub, which you can visit at opendatahub.io. If we think about the machine learning system responsibilities we talked about earlier, the Open Data Hub is a reference deployment and architecture for combining all of these into a self-service discovery environment that you can also reuse with production. The Open Data Hub uses the operator concept, which is a Kubernetes abstraction that makes it possible to deploy and manage software with code to deploy a discovery environment consisting of ways to process structured data, streaming data, and unstructured data at rest, to orchestrate data and training pipelines on this code, and to provide interactive development, discovery, and monitoring environments for the techniques we develop in machine learning systems. Here's how we support a basic use case with the Open Data Hub. On the left-hand side, we have sort of spinning up a discovery environment on OpenShift with object storage, streaming, and a discovery environment. We're doing our interactive work in Jupyter Notebooks. And finally, we're using continuous integration to automatically turn those notebooks we developed into production services like this. If we take those notebooks and pass them in to a CI build, we can actually extract the model training code from those notebooks, train a model in the build, and put it into production as a production service, which we then publish behind a REST endpoint, really limiting a lot of the manual communication and manual reimplementation and sort of difficult and error-prone work that happens in coordinating some of these eminently automatable tasks in these diverse teams. So we have this end-to-end picture here where we have all of these components supported by OpenShift and by the Open Data Hub. And there are a lot of partner technologies in this space as well that fit into this reference architecture. So if you want to start with this open source project and then use commercial offerings for machine learning or data science focused use cases, there are a lot of partners in this space that have technologies that work really well with this. So I'll close with some links to resources where you can get involved or learn more. The first three are links to the Open Data Hub community and the Open Data Hub GitHub organization. And the last one is a video showing an end-to-end machine learning workflow on OpenShift and the Open Data Hub. Thanks so much for your time.
Thank you so much, Will. Very interesting. I believe we have a third poll question. So Chris, why don't you put it up while I get to the questions, because we've been receiving some very interesting questions. All right, here is a polling question. Shouldn't take too long. Let's take just a minute for that. And Omri, get ready for the first couple of questions, because the first two are for you.
Yeah.
Okay, so the first question we got was from Richard, and it was kind of lengthy, so I'm gonna try to read it properly here. How do you prevent mass rescheduling of pods due to the bursty nature of AI workloads? The instability of pods causes workloads to fail randomly, and reprocessing time of these terminated rescheduled pods make these solutions very inefficient.
Yeah, so as part of our queuing mechanism, we have the capabilities also to restore the workloads after saving states. So occasionally those workloads save states. This is called checkpoints in the world of AI development. And when the pod starts again, it continues from the last save state, and therefore you don't really lose your job if pods are terminated.
All right, thank you. And then a question that I got from John, also for you, Omri, is run AI a scheduler or our layer for GPUs or for the containers?
So we're actually doing both. Our solution is implemented as a plugin into Kubernetes and bringing advanced scheduling capabilities to Kubernetes that helps with managing those multiple queues. And then we also built a virtualization layer that allows for provisioning of fractions of GPUs, so you can run several containers on a single GPU as part of Kubernetes. To do that, we had to extend the Kubernetes scheduler to be able to provision fractions of GPUs as well. Natively, it supports only an integer number of GPUs, as well as build a virtualization solution that allows for several containers to run on a single GPU in a secured way with isolation. So we built both this as the virtualization solution, and the solution is implemented as part of the scheduler. So we do both the orchestration, scheduling, and virtualization.
All right, good. We don't have a whole lot of time left. One question for Gil. Gil, I hope you can go off mute quickly. Yeah. Laura was asking if it is possible to use different access modes within the same volume.
Yes, well, we can, when we create a volume or a PVC, we can define which access mode this PVC will support. But when a pod requests to access a PVC, it needs to select one of the access modes, and only one access mode can be used at any time. but we could, a pod could first attach with read-write permissions, then populate the volume with data, and then go down, and a new pod will be with only read-only permission. So yes, it's possible.
All right. And another question for you, Gil. Paulo is asking if it is possible to run the NVMesh management inside of Kubernetes.
Yes, it is possible. If you want to have, the management can be also installed on a bare metal on the node, but it can also run as a pod inside Kubernetes if you want everything inside the same infrastructure. So yeah, it's possible.
All right, good. And then a question for Will. Will, what does it mean to put a model into production for you?
Yeah, so I think this is a great question, and this is one where we've seen really a wide range of answers to this from people we talk to. So for some people, putting a model into production is like what I showed in that architecture, where you're actually taking a model and you're putting it in a microservice so that other application components can deal with it. But many organizations are getting value out of machine learning by sort of using models to answer questions more statically, right? Where putting a model into production is really more, you have a repeatable process that may not be automated, and you're using it to take some data and answer things otherwise. Now, the really nice thing about Kubernetes is that it's flexible enough to support all of these different ways of putting models into production. But really, if you're going towards putting things into a service, I think you want to automate things as much as possible, because that communication loop that you have in many situations between data science teams and app dev teams is really time consuming and introduces a lot of latency and ties up a lot of expensive people.
All right, good. We're at the top of the hour. I see no other questions coming in. Thank you, Will. Thank you, Gil. Thank you, Omri, for your great presentations and for the good answers to the questions. I would like to invite attendees to join us for our next webinar, which is coming up in 2 weeks. We'll have a customer speaking Orange, that is. Again, thank you so much all for being here, and have a great rest of your day or your evening. Bye-bye.